Greetings, everyone. Welcome, and thank you for joining us today for our Grow webinar. Before we begin, please note that comments or questions for the presenter can be placed in the Q&A box at the bottom of our screens. Should our Zoom connection fail, you will immediately receive an email message. Please click on that link to rejoin the webinar. It's my pleasure to introduce Lee West, who for many years has been committed to developing tools that help researchers contribute to the agricultural challenges of the 21st century. Since 2020, Lee has been the Business Development Director for Hiphen Agricultural Imaging Solutions, a company that provides imaging tools for the crop research and agricultural product development community. Hiphen's tools convert images from satellites, drones, and proximal sensor arrays in fields, greenhouse, and lab trials into data that guides impactful decisions on product concepts, regulatory dossiers, and marketing strategies. Prior to his work at Hiphen, Lee led a team of experts at Novozymes to develop fermentation-based agricultural inputs. His focus was on answering specific questions on formulation, business development, and product management. The pursuit of more insightful data led to his interest in image analytics. Today, Lee will discuss ways in which gene banks can obtain more data per dollar spent and also add richer context to that data. The title of his talk is Imaging Solutions for Seed Banks, Characterization of Accessions During Regeneration. Welcome, Lee.
Thank you, Yanni, and thank you for the opportunity to speak to the seed bank community about this technology that's becoming widely used in the breeding community, and that may also likely be valuable in the seed bank community also. And as Yanni noted, my name is Lee West, and I'm the Business Development Director at Hiphen. And we're focused on developing tools to help researchers tackle challenges of 21st century agriculture. She also gave my little biography here, which I was going to give, but I did used to work with Novozymes, and we were developing products for agriculture, so biocontrol products and seed treatments. And as I was working with my teams that were developing these products, we were always looking for the ability to visit our field trials without having to physically visit them, because we had these trials distributed throughout the globe. And as the manager of that program, it was always a little frustrating for me not to be able to sort of participate in viewing the trials and assessing the quality of the work, and also recognizing that there was data that we weren't able to collect, or if we were looking at qualitative ratings in a field where somebody would say that plot's a 5, that plot's a 6, that plot's a 7, and I wouldn't really have any way of reevaluating that. Anyway, that's kind of what led me to looking for imaging solutions and how we could use images to shore up our data sets and to have more confidence in our data sets and to learn new things. So the pursuit of this more insightful and interoperable data led to image analytics, which now helps me shape the Hiphen solutions in the context of product development. So the products meet the needs of end users like breeders, crop protection, product developers, scouts, production farmers, or in the case of this community, seed conservationists. There we go. When Yanni first asked me about discussing image analysis for seed banks, I must admit I had to do a little background to understand the process. And it started with this nice seed crop trust graphic, which kind of frames the context of, let's see, where are we here? Frames the context of regeneration and characterization within the sort of between prospecting for biodiversity and leveraging that biodiversity through crop breeders. Whoop. I'll keep my discussion around wild crop relatives as diversity banks for crop breeders. My understanding is that seed needs to be regenerated to maintain viability. So they have to be grown out on some sort of cadence, be that 10 years, 15 years, 5 years. I guess it depends quite a bit on the type of crop. And also also the seed banks need to be able to supply breeders and supply their needs. And so seeds may need to be multiplied, which leads us to characterization and why Yanni reached out for a discussion on image analytics to improve the characterization process in the first place. The value of the process is, of course, to help the customers of the bank services to target characteristics they want to breed into their existing varieties. Things like stature, architecture, and color, but also more complex characteristics like drought or heat tolerance or disease resistance. While these accessions are being grown out, there's a unique opportunity to capture phenotypic data that can accomplish the characterization component of the seed bank mission. To prep for this, I looked at some of the characterization panels in Genesis, which is, I believe, the crop trust tool where you capture the all the phenotypic data and quite a bit of data actually. I guess there's bioinformatics added there too. And it looks like a great database, and I was a great database. I was impressed by the level of detail in some of the data sets, and the amount of time that must have been required to characterize these different sessions. I estimate just from kind of browsing through, looked like there's about 500 characterization data sets, which are necessarily different, of course, for 40 different crops. And it looks like wheat and barley represented nearly half of those phenotypic data sets. Although this is a lot of data, I think there are significant opportunities to augment these data sets and create data sets that are more interoperable with some consistent imaging solutions. Please note that I said augment, not replace. I think there are traits in those data sets that I think are quite important and will be quite challenging to create automated image analytic pipelines for. Things like flag leaf attitude, seed weight, pubescent type may not be attainable or worth the effort of automating. But things like plant height at one or multiple phenological stages, growth rates and dynamics, flower timing and intensity, these all can be assessed in a more principled way with images. And the subsequent data will be more consistent across sites and also consistent with the breeder's own data if they have started using these tools, which are rapidly becoming domain standards in the crop research and breeding communities. Which leads us to how a breeder is thinking when they look at assessing seed bank assets, or as Nigel Maxted noted in his talk, genetic resource centers, to check out some germplasm. So a breeder approaches the resource center with a query to identify the material they're looking for from the millions of accessions that are cataloged in the repository. So what are they looking for? I think often it's going to be something like drought tolerance, disease resistance, pest tolerance, high protein, nutrient use efficiency, et cetera. And how do they find the right accessions so they can check out material that is most likely to confer the characteristics they want to propagate in their breeding lines? As Felipe Basso noted in his Grow webinar, better understanding the material you're bringing into your breeding lines allows you to start searching more efficiently for those game-changing champion characteristics that lead to novel parental breeding lines. So this is a graphic that I use when I'm talking to breeders about where image analytics fits into their programs. And I should have added on regeneration above nursery trial, because leading into the nursery trial, the things that you're testing in your nursery trial are going to be crosses and where breeders are going to be utilizing WCRs, wild crop relatives from the seed bank databases. And so high throughput phenotyping always brings value and better understanding to GDE interactions within your field trials. Whether you're at the regeneration stage, the nursery stage, you've reached yield trials, or you're doing, some sort of in situ conservation efforts. So you can make better advancement decisions on which percentage of your trial population you want to advance to the next stage and generate new crosses. I'll touch a little bit later on how researchers are working on phenomic prediction models, similar to genomic prediction models, that will allow breeders to more effectively evaluate the heritability of characteristics in their lines and potentially do experimental in silico breeding eventually. But let's get down to sort of in practice phenotyping that might be applicable here to the seed conservation community. So in practice, what does phenotyping look like? I'm going to be talking mostly, here's where I'll start discussing how we apply imaging analytics to breeding and exploring how image analytics might apply to genetic resource centers, both seed banks and in situ conservation centers. I'll frame the discussion around the three pillars of an image analytics program. We'll talk about acquiring images, so image acquisition, trait extraction, and give some examples of some traits that we extract on a regular basis that might be relevant, as well as I'll show sort of a broader view of all the traits that we're supplying to breeders. And then data visualization, image query, and data science applications. So once you've extracted the traits, how do you put them to use to make decisions that you need to make? I'll suggest ways in which these tools might be applied to regeneration, but really I'll be describing tools and processes that we apply to breeding currently. And we'll be kind of querying you for input on how to deploy this technology to address the challenges that you have around efficiently characterizing the accessions that you care for. Before I touch on vectors, I want to frame up the 6 dimensions of phenotyping. This framework helps us think through options for sensors and vectors to carry and orient sensors. So X is a one-dimensional view like you would get with a LiDAR or a line scanner. Think of a microtome, if you ever used a microtome where you're taking very thin slices, looking at them, and then putting those back together. So these images can be combined to create very accurate 3D images. Y is the second dimension, which, like a regular camera, gives you a flat representation of a field of view. Z is the third dimension. There are many tools to generate 3D images, from lasers to stereo vision cameras to techniques like structure for motion, which allow us to create 3D recreations of plants and fields from imagery. The fourth dimension is spectral range. Choices here include RGB cameras, narrowband multispectral cameras, and all the way up to complete range narrowband cameras, often referred to as hyperspectral cameras. So the angle of orientation is the fifth dimension, which relates to locating sensors in relation to the area of interest on the plant so that you can see it. And of course, the time component, things like phenological stage, diurnal cycles, speed to canopy coverage at specific thresholds, or in the case of photosynthesis assessment, where we measure the signal decay over time. Time is an important component to phenotyping program planning. So while we work with any image acquisition vector, including greenhouse and lab scale phenotyping systems, since we're talking about characterizing accessions during regeneration, I'll focus on field image acquisition. I'll start by touching on the 3 main vectors to carry sensors to the field. And by vectors, I mean just something that somehow gets the sensor to the plants, that carries it, basically. And I'll start by touching on the 3 main vectors: drones, tractor-mounted sensor arrays, and handheld or proximal imaging tools. These vectors, I'll go back here. So these vectors each have strengths and weaknesses. Oh. These vectors each have strengths and weaknesses, and breeders deploy them on the needs of their program. Drones are the most efficient way to get across a field quickly, and where there's thousands of plots, it's often the tool of choice for breeders. Drones can carry a variety of sensors from RGB and multispectral cameras to LiDAR and thermal cameras, but they can't really carry all of them at the same time. There are already well-vetted and automated processing pipelines that allow for rapid data delivery, and they could fit well with both in situ conservation and regeneration characterization programs. For high-resolution applications like counting wheat heads or doing detailed disease assessments, drones are not the most effective tools because it's difficult to access sub-millimetric spatial resolution for challenging trials, though they may be effective enough to given the efficiency of operating them. We'll talk a little bit about that sort of trade-off here. Then we have manual ground imaging systems or proximal imaging systems. Because they're so close to the canopy, they have significantly higher resolution for traits that need sub-millimetric resolution. The specific tool in the picture here is Hiphen's literal tool, which is specifically designed to count wheat heads and assess fusarium head blight. There's also a side-facing camera, which allows better views into the canopy to detect discrete objects. And on the downside, this unit must be carried to the field by a person and has only a moderate throughput compared to the drone. The final vector I'll mention here is tractor-mounted sensor arrays, or a rover. This rover can be a fully automated robot or simply a tractor with the sensors mounted to it. By attaching a sensor array to a tractor, you have power, which means you can drive more complex sensor arrays. You can capture spectral imagery, LiDAR, and thermal imagery all at the same time. You can also use active lighting to create very consistent images. Of course, this is slower than a drone, it's faster than a manual system, and it's significantly more expensive than either of them. These types of units tend to be deployed for high-intensity phenotyping of high-value material or where complex problems are being explored, things like drought tolerance, disease dynamics, etc. One of our tractor-mounted sensor arrays is at ICARTA, and we do a lot of work with CG centers in their breeding programs, helping them with their breeding programs. There are also several universities and government research organizations that operate these type of systems also. So a little comparison of these systems. When we do these comparisons, we're looking at three dimensions that we're focused on when we're making a lot of these choices: are spatial resolution, how big are the pixel sizes. From a satellite, we're looking at 3-meter pixel size. So each pixel is 3 meters by 3 meters. So you really don't see plants very well. It's just there's too much noise in that. But you can still get a lot of really interesting information out of that. A standard drone, you get about 3.5 millimeters of resolution at a reasonable flight pattern. With the proximal sensor, you can get down to about 1/3 of a millimeter of resolution. And with phenomobiles, because they have more power, they have active lighting, and we can control the cameras even more precisely, we can get down to 0.1 millimeters. And if I knew my metric system better, I'd probably use a better term for 0.1 millimeters. But once we get down past millimeters, I'm not too fluent. But anyway, the point is that there's a gradient of resolution here. Spatially. Spectrally, there's also a gradient of resolution. And those are choices you make between, I mentioned the RGB cameras, the multispectral cameras, and hyperspectral cameras. A lot of people hear hyperspectral and they want to try these hyperspectral cameras. But when you start thinking about hyperspectral cameras, you have to start thinking about different servers, different data management systems. You have to think about gaining access to high performance computing power to handle those kind of images, because a hyperspectral camera can take 900 images for every image that you take, right? Because each band becomes a separate image. So they very rapidly create these data cubes that are very, very, very large and hard to move. And so anyway, but those are choices that we're making. And then also temporal resolution. So temporal resolution, things like satellites are crossing, if you're using these low orbit satellite constellations like Planet, they're going to be taking pictures of every point on the planet every single day. And we use these a lot for production fields or seed multiplication processes where you're growing larger areas and you want to maybe do an irrigation study, and you have irrigation blocks that are 40 acres or 60 acres. And you have several of them that you want to do some comparisons on. And for that, satellite is a great tool because you get readings every single day. So when you do a dry down, you're going to get an image every single day. Now, in theory, you could get images every single day with these other tools, but it would be a lot of work to get them out there and operate them. So these are all factors that are a critical part of the equation when considering which vectors are the most appropriate for the objectives and the scale of the research initiative. There's an inverse relationship between throughput and resolution, and resolution drives access to more complex traits. So finding the right spot to access desired resolution and get the throughput that you need is an important decision, and it's something that you're often making compromises on. So I see throughput as being a major determinant in vector choice between a drone and something like a littoral or a proximal sensing unit. If you have less than 1,000 plots, it might be worth exploring a manual system for the increased spatial resolution. It has nearly 10 times the spatial resolution. So, you get a 0.36 millimeter resolution instead of 3.5 millimeter resolution, which allows greater attention to architectural characterization, disease assessment, and organ counts, wheat heads and fruits, etc. On the other hand, it takes a lot longer to get through a field. If you've got 10,000 plots, it's just going to take many days to get across a field, so you'll probably lose some of the dynamics that you're hoping to capture with that. One thing to keep in mind is that there are many situations where we'll fuse data sets, basically collect images from different vectors. For example, we'll use this maybe to calibrate an algorithm. So we'll use a ground-based system for high resolution to most accurately, say, assess a disease and attempt to correlate with a less direct trait that can be assessed with a drone. So for instance, we might look at, we've got a project where we were looking at Cercospora on sugar beets, and we had a proximal sensor that was taking measurements and assessing the disease. And then we flew a drone over that same field on those same days. And what we found was we could get a pretty good 85% correlation with the ground assessments. And then you can make the decision, you're going, is 85% good enough? Considering that means that we can fly a field and collect a set of data and get this disease assessment in a matter of, less than an hour, as opposed to sending a team out in a field for, an entire day to get those same assessments. And so those are the kind of decisions that you make when you're assessing how you want to approach that. And so by fusing data sets, you can kind of have some data to make those decisions. We also complement data sets. So you may not need submillimetric resolution through the whole season. So you'd use a manual vector for a subset of the collection dates and fly a drone for all the dates, so you can have continuity of data across time while also accessing submillimetric precision for certain time points, maybe where disease is present or for wheat head counts. Another example we commonly use data fusion is when we use satellites for production fields. When we're tracking fields with satellites, we often also design a drone program to complement the satellite imagery and gain insights and interpretive guidance to the satellite imagery. The satellites offer high temporal resolution basically every day. Well, minus days with clouds, but the spatial resolution doesn't allow you to actually see the plants. The drones then complement that satellite imagery with targeted flights to take closer look at the trouble spots indicated in the satellite imagery. So once images are collected, the next step is extracting data from the images. Okay, there are several non-trivial processes between, like stitching images into orthomosaics, georeferencing plot maps, clipping plots from raw images, etc. But all of this is getting to the good part, which is getting data from the images. So I'm going to kind of skip over some of the processing steps, but just so that you know that there are some non-trivial steps involved before we get to start pulling information out of the images. So I've selected a few traits that I think might be interesting for characterizing the broad differences that that might be included in regeneration plots of wild crop relatives, where you may have much broader diversity of shape and size and maturity ratings and things like that than you would in a breeding trial where the material is already pretty streamlined. So while phenological stage detection would be very interesting to understand how the different accessions, how quickly they mature, how quickly they reach certain stages, so that you could, maybe if you needed an early variety, you could target something that seems to be flowering earlier, or you need a late flowering variety, you could find something like that, but you'd have some indication that you could use. So while maturity is an important trait for several crops, I'm not sure it has the same meaning in wild crop relatives, but again, still valuable to understand the crop when the crop is hitting certain phenological stages, if it's doing it quickly or slowly, what's the speed to canopy closure, what's the time to first flowering, etc. And these things can be captured in time series analysis. And so I think that phenological stage detection is an important thing for accession characterization. Another trait is an important characterization trait would be disease detection. And this can be very important information for breeders to have access to. This is often what they're looking for when they're trying to breed new disease resistance into lines that are high yielding. So this can be a bit tricky as there are so many different crop disease complexes. So there are not production pipelines for many of those complexes. But we have another tool I'll show you in a minute that allows you to do your own visual assessment from the images. Another trait of interest is early vigor, and this characteristic can be an important indicator of field competency. By doing a set of acquisitions early in the season, you can also derive a time series trait called speed to canopy closure, which can be critical for weed effect reduction. And in many areas where herbicides are not either available or allowable, this can be a really important trait here. Another key trait that we can assess with drones or proximal sensors is flower count and the dynamics of flowering. So this is another trait that's relevant for most crops. And when doing counting, we can also classify several dimensions. For instance, bud stage, flower stage, sunflower seed filling, and to increase the granularity of the counts and the dynamics. You'll notice up in the upper corner, you can see how we build acquisition protocols. In this case, the example specified a DJI Zenmuse P1 RGB camera, which has a higher than average resolution sensor. I think it's a 40 megapixel camera. So we know from experience that the size of the inflorescence can be as small as 40 millimeters, and the flowers can be as big as 300 millimeters. So we can calculate that we need 4.5 millimeters of ground resolution to confidently count and classify this trait. With the specs of a P1 sensor, we'll recommend flying at 15 meters for the first flight in the bud stage and 18 meters for any flight after the majority of the petals have emerged. The ability to understand this GSD, sort of a spatial resolution, in relation to sensors and vectors is critical to making decisions on the sensors and vectors required for specific programs that require specific traits. So now I'm going to show sort of a broader crop trait matrix. And again, this is what we have sort of commercially available for breeders right now. But we have a catalog of traits in production from drones that cover a wide variety of crops from maize and wheat and sorghum to sunflower, rice, and strawberries, to name just a few of the crops. And so, this crop matrix basically is our production traits. Basically, that means that these are things that we do regularly. We're doing this all the time with breeders. So all of these traits are very well vetted. We can do them quite simply, and we classify these traits into 4 categories. We have trial quality traits, things like plant count, lodging, plot heterogeneity, gap assessments that allow you to eliminate plots if they're not of adequate quality. Canopy development, and this includes things like green cover, early vigor, maturity, speed to canopy closure, flowering. Biomass proxy traits. So these are things that include plant height, biovolume, leaf area index, chlorophyll content, and a wide variety of vegetative indices. We always say biomass proxy because one of the things that we really don't read very well with images is the content of water in a plant, which to do biomass, you really need to know the water content. But in lieu of that, creating a biovolume measurement we found has been a very useful tool for assessing the size of different plants. And final harvest index and quality traits, things like organ counts and harvestable area. Might do sorghum head counts, sunflower head counts, wheat head counts, maybe count tomatoes on a tomato plant. And then sometimes we'll do a harvestable area assessment where we'll look at the plots and we'll recognize that there are certain holes in the plot for plants that didn't grow in well. And the researchers will go back and try to determine whether they think that actually reflects the germination rate of that particular germplasm, or if that maybe was a planting error. And so they want to remove that from the assessment of yield, and they might say, hey, it looks like we misplanted and we lost 10% of that plot because we misplanted. So when we harvest whatever 100 units from 100 units per hectare, we're going to adjust it to that 100 units was grown on only 90% of that plot size. So when we scale that out, they can make adjustments. We're actually working with some groups where the combine operator, as they're driving up to a plot, they're looking down on the plot and they're going, that's about 70% of the plot is there. And that number is being recorded. And then later on, they're assessing that. And when we're talking to that group, that's kind of how that trait became developed, because they really needed a more principled way to do that. All right. And now, so that's from drones. Now I'm going to talk a little about Literal, which is the proximal sensing unit, manual sensing head. And we also have a crop trait matrix here. This is really Literal is focusing on really high resolution applications. So those things like I mentioned wheat counting from drones, and we do that, but you have to have very specialized drone equipment. So it's not your standard drone equipment. It's much easier to do it from a manual system like Literal, which has much higher resolution. And actually, that's what this unit was designed for. So the Literal tool is tool that's been in use by Arvellus in France for the past 4 years. So it was primarily developed to count wheat heads in plots and assess fusarium incidence and severity. We worked with them this year to make the tool more broadly accessible geographically and across more crops. It'll be available in January, and it'll be an excellent complement to a drone, and possibly even a replacement for a drone for areas with, say, less than 1,000 plots. I'm using that number very loosely. I think even with larger trials, it may be a viable tool. You just have to weigh it against how long it will take to collect the data from the manual system versus the drone. So getting down to data visualization, image query, and analytics, Hiphen's mission is to make image analysis tools accessible to the agricultural research community that's working to solve the challenge of 21st century agriculture. To this end, we have developed our platform, Cloverfield, to make using drones, littoral, and tractor-mounted sensor arrays as frictionless as possible. You can simply drag and drop image sets from your drone, add a plot map, and as my French cows show up as a dot on the map. As you can see, we work on projects across the globe, and oops, um, we work on projects across the globe, and our project teams work with geographical and organizational diversity from big companies to universities to governmental organizations to NGOs, and we're skilled at working with you wherever you are in the world and at whatever stage you are in your imaging solutions journey. When you click on your trial, you'll see a heat map of your trial that allows you to quickly, battery running low, that allows you to quickly identify top and bottom performing entries. And you can click in any plot and experience the magic of image query. This was always a dream when I was managing trial programs, where I could not always see every trial and certainly couldn't grab images from any plot at any time to emphasize a point about trial entries. Marketing and communication teams love this feature, even if the researchers often say, just the facts, please. But I feel that even some of the most principled researchers will still take a look at the images to help them derive their interpretations of data. So, oops, yeah. Now, most of the time, we'll automate pipelines to extract data from imagery. But with the Researcher's Eye tool, you can fly a drone over a field, upload an image set, and then come back and rate the plots with a cup of coffee in your hand, listening to your favorite motivational music in your office armchair. This is especially interesting for anyone involved in crop protection projects where you're using qualitative ratings. I've viewed data tables full of qualitative ratings for many years and always wish I could back check the ratings, but there was no way to do that. Well, here's the tool I was waiting for so many years. We can customize the scale with either qualitative or quantitative scales, Joe's powdery mildew score or Meg's early vigor rating. You can have a picture of every scored plot alongside the data. If you have many thousands of plots, we can discuss how we could use your classification annotations to create a model by scoring some small percentage of the plots and then scaling to the rest of the trial. Of course, the most valuable piece of information are the data extracted from the images. Though this tool is not meant to replace your data analytics process, it's designed to provide a quick look at the data in several ways to allow you to start your data exploration quickly and easily. There are too many features to cover here, but in case you didn't notice, I'm really fond of our image query tool. And I want to mention another image query component here at the bottom. And if you have replicated trials, you can scroll through each of the entries reps and quickly and easily. And if you find anomalies in the data, you can check the plot. And if you decide to eliminate it from your analysis, you can have a picture to support your decision to remove the plot. So I'm going to really briefly talk about phenomic prediction because I'm not an expert in it, but I think it's important for this community because phenomic prediction involves estimating discrete traits from commonly measured traits through advanced data science methodology. This is HELEX is a EU project that we're looking at estimating seed moisture using phenomic prediction models from raw sensor data collected with a drone and a high sensor. There's 18 groups that we work with on this project, so it's a complex project. I want to add a caveat before going any further. I am not an expert on phenomic prediction, so my description is that of an agronomist trying to explain a data science project. So operating slightly out of my domain here. Step that we go through here is we isolate the organ, which is something that we do all the time. And then we create a lower dimensional representation of the sunflower heads, underlying structure, and potentially hidden relationships, and generate
Sorry, everyone. I think we have some communication problems, and we'll just be waiting a minute for Lee to get back on. Thanks for your patience. Yeah, sorry about the interruption. Lee has just dropped off, I believe. Let's just wait until he comes back. We do have a good number of questions coming in. Some of them you put into the format as you registered, and we have those. Thank you very much for putting those in. Others, please take this time to put in the questions and answers and any comments that you might have in our Q&A. And I think Lee is back. Thank you very much, Lee. You're muted at the moment, so please unmute yourself while we get back. Thank you.
okay, I'm unmuted now. Okay.
Yeah, thank you. Yep.
Well, I was going into talking about phenomic prediction, and I'm going to kind of move through this. I think that the real point here is that we're working with similarity matrix and kinship matrices. And I think that's going to be something that may be very valuable when selecting accessions and actually characterizing accessions that may be similar to each other. Let's see, where am I here? Can I still control this? Let's see. There we
Yeah,
go.
I think you need to reshare because it was dropped. And
Okay.
so just please share your
Gotcha. Okay. Well, I was at the end anyway, so what I'll do is, let me get this back up here. Share screen. There. Okay. So I'll go back. So with the phenomic prediction, basically, we were able to show pretty good correlation between predicted values and that we predicted with phenomic prediction and some ground measurement data that we also took. So again, that said, basically the take-home message here is that these models, I think, are going to be valuable, potentially valuable. I still say potentially because I'm not exactly sure how well they're going to work on something like wild crop relatives. But by building these kinship matrices, sometimes we may be able to extract some interesting information. So that was really basically the end of my talk. I want to, kind of just share a little bit about the breadth of work that we do with both industry partners, many of them you'll be familiar with, as well as research center partners. So we work with several of the CGE centers, everybody from ICARTA and CIMMYT and IRD and who else? ICRISAT and many others. And so we're very tied in with the European phenotyping network. And since I've joined, we've become more integrated to the North American and South American centers that are doing work. And with that, I will kind of close, and I hope that I have I hope that I've sowed some seed for thought and that we can kind of figure out ways that we could help with this process in the future. And so I look forward to hearing from you. My email address is now here at the bottom of this slide, and would love to hear from any of you if you want to kind of talk through any of the things that I mentioned here today. Thanks. If there's any questions, I'd love to get to those.
Yes. Thank you. Thank you very much, Lee. Yes, it has been extremely helpful to see in some of these slides the basic breakdown of the vectors versus resolution versus cost. And I think that that is a huge contribution to gene bank staff who are kind of struggling to decide, well, do I buy a drone or is it better to go with satellite? So thank you very much for putting together the presentation. And I also really appreciate that you are trying to cross this line between having large fields, working with breeders, and then cross over with a gene bank with much more diversity and plots that are much smaller. So I appreciate that you're trying to accommodate something you're not normally used to working. And making the effort to try and present something that is useful, very useful for us to try and consider in the future. As you say, we need more principled ways of bringing data in and putting them up in Genesis so that there's a more harmonized way of comparing things. We have a number of questions. Feel free if you already think that you've addressed these because these were on the format, so we had a
Sure.
chance to discuss them. So feel free to just say that has been discussed, but I will read them anyway. The first one is, what traits can you measure or characterize in the field, and what are the requirements to measure them accurately?
So I would have to go back to the sort of trait matrix here. This is not a complete list. There's more traits that we capture. There's more crops that we work with. But I think hopefully I answered that. Hopefully that question came in before I started talking about this.
Right. So what resolution do images have to be for field application of the tool using satellite imagery?
Um, so if I may be misunderstanding the question, but we use satellites when we're dealing with large blocks. When I say large blocks, I'm talking about things that are, maybe at least a hectare in size. And people will often do that for, say, variety trials or strip trials. Sometimes we can do that if they're large enough strips. And so, 3 meters is about as good a resolution as you can get. There are satellites that'll have 0.5 meter resolution, and we have some proposals in with the CG teams to look at some of that, but they haven't been funded, and so there's some hard work. Those really high resolution satellites are not really designed very well for crop measurement, and so there's some what I would call fusing between different satellite constellations that will have to happen to make those really useful for agronomy.
Okay, so I guess a side question to that is, we deal with rows that are maybe 1 meter wide by 5 meters long. And at times
Mhm.
we even have to go down to a hill plot because that's the area that you have and you need to regenerate very quickly, many accessions very quickly. So in that case, you would drop down to it's a phenomobile, or would you use a drone for that, or literal?
A drone
But
can still
if you have
capture
a
that,
smaller
depending on
plot,
what
what would
traits
you
you're
use?
looking for. Yeah, we work with breeding nurseries where you are sometimes dealing with, 1 meter by 1 meter plots. And sometimes they're even smaller than that because they don't have enough seed. So,
Right.
um,
Okay, so that's great. So this is exactly what we're looking for then. How can I quickly be able to establish potential characteristics of accessions to enhance utilization? That's a very broad
um,
question, but
so enhanced utilization so that you can get the data quickly. Is that enhanced
well, no,
utilization? So,
utilization by farmers, by researchers, by breeders.
gotcha.
So what
So I think
characteristics
that's where,
that
I
specifically
think,
interest others? Yeah.
yeah, I think that this is where Genesis looks like a really good database. And I mean, ultimately, what you're going to be doing with this data is moving it into some database or data lake where people can access it. I mean, they can certainly access it through our website, right? This platform that we have allows you to to look at your field trials. I mean, I think I can pull up a live of that. Let's see if I can pull that up. And you can certainly go to our platform, but it's probably not the best place to store your data long term because you're storing this long term. We're going to archive data eventually, just because we have to move it off of our databases. But so I showed you this is live. Of course, it's going very slow. That's why I probably got cut off. I don't have a good internet connection right now. Or we probably are doing some something at the office that's hogging the network capabilities. But basically, this is one place that you would access it quickly. This is the first space, because from here, then it would be downloaded into a database, and we can set that up with APIs if we have if we want to have a real consistent program, or we can do things with or we can just download it as a CSV, which is what most of what you have in Genesis, where for the phenotyping things are just CSVs full of data.
Okay, so this is kind of a two-part question. There's two questions, but they can be actually put into one. What are the non-online software tools that can be utilized by gene banks? Do you know of any online tools?
Online tools. Well, I'm not sure exactly what the ask is. Non-online tools, so things you could download yourself and have them on a laptop or something like that. Really, there aren't any good solutions. I will say that over the past couple of years, we have bought out a couple of companies that were trying to do that. They were trying to put out a drone program, and then they basically couldn't get it to work well enough. And so we worked with them to transition their customers over to this online platform, because it's very difficult to maintain desktop software. And that's why most, software companies are basically online platforms. And I know that's difficult when you don't have good internet access. We do have some offline tools that allow you to load data that will upload when you reach internet connections.
Okay. The other part of that was any free tools that can be used, for example, by national banks who don't have a big budget as of yet. Are there any free tools that can be used to manage gene bank data?
Well, there are sort of free tools that can do some drone image processing. But those require, sometimes free tools are more expensive than using commercial tools, because really to do that, you have to have staff that's capable of handling open source and putting together, has to be very competent with coding.
Right.
But
Yeah.
there are resources. Plant CV at the Danforth Center is an open source. You can get an open source, modules that you have to put together yourself. So it's not automated. It's not a pipeline. It'll take a while to do. And then there's another one, Field R, which was I think University of North Dakota has that, and they tried to do that, and but I don't see them as much anymore. So I don't know if they're still as active. So those are free resources as long as you have significant skills in coding.
Right. Okay. So this next question has to do with trees and plantations. What do you have for trees? For example, an orchard like pears, anything about flowering, fruiting? Have you had any experience with coconut plantations, things like that?
So with things like pears and some of the orchards that you see in Europe, apples, pears, peaches, we do have some units. We have some tractor mounted sensor arrays in orchards. We fly drones over orchards and are often looking at flowering dynamics. With the tractor mounted sensor arrays, it's really on a little trailer that goes behind a tractor, looking into the canopy, and we're usually trying to count fruits. And It's a little bit more intensive a resource, but it's a very powerful tool. And it captures a lot of information. You know, you can we put lidars on that so that you're capturing very accurate architectural information about the tree,
Mm.
location on the branches of the different fruits and flowers and things like that. So yeah, we do work with orchards. Haven't done much with coconut. I don't think I've seen a coconut project that we have. But we work with so many crops in so many different places that I'm pretty confident that there's information that we would have to basically, what we usually do is we get somebody to take a drone picture, just take a picture at, 30 feet above the crop or 50 feet above the crop and send us a picture, and we can start to look at what we would start extracting from that, what we could do easily, and then what would take more time.
Which image acquisition platform will be the ideal for the pre-breeding program, as the number of lines will be huge? So of the vectors that you mentioned, which one would you
So
advise?
when you have, huge numbers, drones are the only way to go, really. Um, we were working with Simit and their nursery, and they had 120,000, I think, a session, things that they were testing. And, there's just no way to walk that with one person. Well, one of the things that we did talk to them, and they were kind of like, well, we really like this ground thing as literal. But to do 120,000 plots, it's just, you can probably do with that system. I think in a nursery, you could probably do somewhere around, I'm going to say 150 to 200 plots per hour, right? You
Mhm.
start doing the math, and it takes a long time to do 120,000. And they're like, well, we usually deploy 20 people out in the field to do that. And so then if you start doing 20 people, I don't know, there's some math involved there.
Yeah.
So
Um,
drones for
Drones would
100,000,
be the way to
you're gonna have to
go.
go with
Yeah.
drones, yeah.
So you had mentioned that water was one of your big challenges to measure that water for biomass, for example. So
Mhm.
this question has to do with that. Can we estimate biomass of a crop in the final stage, as the leaves will decrease, and translate that water to grain yield? Is there anything at the end of, towards harvest time that can be done to estimate biomass?
That's an interesting question. I don't think that we've really done that, but you're right. Ultimately, you're looking at, a pretty when plants are senescent, and those sunflower plants, when they're senescent, the primary weight is the head. Um, but that'd be an interesting question. We'd have to take a deeper dive into that, but we have not done that.
Okay. Say one of the gene banks is interested in the literal platform. What would be the approximate cost that they would have to incur if they want to reach out to Hyphen and start implementing that?
So I think the price here is I think it's $20,000, and that includes a year of processing. And then every year post that, it's about $5,000 a year to process images,
Okay.
basically all the images you can take.
Um, Here's another one on, thank you. They say, thank you for the presentation. Can imaging be a substitute for characteristics which have manually been measured, for example, like height and or biomass?
Yeah, I think so. I think particularly for plant height, um, that would be, it's just a much easier way to do it. And people always are like, well, I don't know if, whether it's going to be the same as the old plant heights that I've taken. And it probably will be a little different because it's going to be a different protocol. But again, it's a more principled thing. And so one of the things I used to do was we would always have plant height measurements as part of our field trials. But what we found was the coefficient of variance when we run ANOVAs was always really big. It was way too high for us to use it. There's too much noise in the data. And
Hmm.
what we find with a more principled sort of assessment, the CVs come down significantly to the point where they're what we would be in the range of when we were running trials, less than 15, because field trials, we accept a pretty big CV. But if the CV was less than 15, we would use that parameter as a we would consider that a good parameter. We could use it in an analysis. If it's above 15, you start to really wonder about whether you just got too much noise to have any confidence in the any analysis.
Yeah. So this is a really interesting question from the International Potato Centers, and you're going micro. So they have an in vitro collection, right? It's kept in tubes, and they're small plants that are kept there between 6 months and 2 years. And they
Yeah.
constantly have to monitor for vigor before, they reach physiological senescence, and they have to be propagated to be able to maintain the in vitro collection. This is in a lab,
Mhm.
in a growth chamber,
Yeah.
under light and heat, right? So
Yeah.
specific environmental conditions. So these little tubes of plants or potatoes or sweet potatoes are kept in this environment. So this person's question is, could you give us any advice to apply image phenotyping in large scale for in vitro collections? Some image monitor tool would help enormously in monitoring the vigor of the plants, through time, because they might have, 10,000 accessions in this in vitro collection.
Sure.
Would something on the tube, for example, or something over the tubes be able to give a better sense of vigor and when physiological senescence is setting in?
So those are types of questions that we love to talk to people about. It's easier if we have a picture that we're looking at and going, okay, here's the setup. Because it's also really hard to know, do you want to take them out of a growth chamber? Are they, are they in some sort of chamber that you have to remove them from? Do you want to leave them in place and move cameras to them? Those are the sorts of questions. We have a whole sort of set of questions that we work with people who have indoor or greenhouse or lab or growth chamber applications they're looking for that we would usually do a check down on. So we'd be happy if you grab my email and you have a couple of pictures that you can send to us. We'd be happy to grab a conversation and look at those pictures and think through that with you.
Yeah, that would be really
Whether you do it yourself or whether we, design an engineering solution.
yeah. So a couple of requests for the presentation. Yes, the presentation will be up in our Grow Webinar website. Another question about rice. There was rice in the drone production trait slide. There
Yeah.
is rice there mentioned. So when you have a chance and look at the presentation, you'll be able to see rice there. From IITA, thank you for the presentation. How do you decide flight height for different crops and for different phenological stages from early to late maturity?
So we're generally trying to figure out exactly what trait we're looking for. If we're doing things like vegetative indices, we can fly at pretty high altitudes.
Mhm.
But if we're looking for, let's say, sunflower counts or sorghum head counts, or maybe even harder to do things like tassel counts on maize, we need more resolution. And so we've done enough of this where we actually have a recommendation by trait. So if you come to us and say we need, we want tassel detection on maize, we might say you need 2 millimeters of resolution. If you need, sunflower head, for sunflower heads, if you don't need the buds, if you need the buds, you need 4.5 millimeters of resolution. If you don't need the buds, we can get away with 5.5 millimeters of resolution. Um, and and then what we do is then we have to figure out what sensor you have. So, different people have different cameras on their drones. And so then we would make that calculation of what altitude you need to fly at. So it's a very calculation based decision or protocol that we build.
Okay. We have a few more. Are we doing okay? We can
Yep, I'm
continue.
good. I've got
All right.
time.
Sounds good. So this question has to do, you receive all this data, large amount of data that is analyzed, and can you take us through to see how then you receive, or how can you conclude about what data is important for each accession? So how do you analyze then accession by accession, or do you receive data on a particular plot, or how does that happen when you have all of this input of data and then it has to be narrowed down to an accession to be able to make a decision on something?
So let me see real quick. Can I grab the screen back?
Sure, yes.
So this is a live view of our platform here, and this is a demo thing that is just with some public centers that I can share data. One of the good data sets we have here is on, oops, not there, select site, go to this one here. So this is the experience. You'd have a dot on a map, you'd pull it up here, you'd see your plots. You can kind of zoom in on them. I want a little bit, I don't want to see as much of the heat map, but I want to see more of the plants. I can bring that down. And then you want to look at the analytics here. We've got analytics in here. So you can go by your different traits, and you could, let me see if I can get rid of this here. Um, we also have an advanced filtering tool, which has moved. Let me see if I can find it here. We just did an update. Here it is. Okay. So if you wanted to look at these, let's just say I want to grab all of these things. If I want to look at, say, selecting varieties, let's say, that have a green cover, have a high green cover. So I might, look at, I might focus on this group right here. And then now I can see, now I want also plants that have that kind of green cover, but also have a, a high, relatively high biovolume, or max plant height. I want fairly tall plants. So now I'm scaling down, and now I've just with those two traits, I've kind of narrowed down the field. I can't move this bar here, huh? Oh yeah, I can. I've narrowed down from 147 traits, I think is where we started, or down to maybe 31 traits. I can't see my numbers here.
Okay. Yeah,
But
that's what.
these are basic tools that we've got it built in here. But I always note that these are really basic tools. We want to be able to very quickly look at these. But really, if you're going to do sort of your deeper dive analysis, you can always just download the results as a CSV. Like I'll download them like literally right now. So I'm going to download the CSV. I don't have that previously downloaded. I just downloaded it, and now let's open it up here. There it is right there. So I just downloaded all that data. So this is in a format, it's a semicolon delimited, so I could break it out into a regular spreadsheet with easily, or you just load this in if you're using R or something like that, then it'll read this data very, very easily.
Wonderful. Yes, very nice demo. I think we might cut and paste this and put it in the demo in your presentation as part of what you said, because I think very important. I think very nice demo. Thanks for that. We have a couple of more. What are the prerequisites for a gene bank to implement these solutions? Do they need special labeling of the accessions or any other considerations in order for this technology to work?
I mean, basically, if you're growing it in the field and you have a plot map that identifies each of the accessions, I mean, like when we're working with big breeding companies, they'll often code it. They don't want us to know what that is. And so we just create an XY axis, and then, each plot has an X and a Y value. And then you can use your secret decoder ring to figure out what that is. But I think that you guys probably would be better off sharing the accession so that it goes straight into your database. It's easier to capture. So really, there's not a whole lot of requirements other than having a tool to acquire the images. And again, we usually want to work with people, to acquire the right tool for their specific needs. Yeah.
Okay. Yeah, several of the ones here have already been answered during your questions, the previous questions. So there's the last one here I'm gonna take. In use, this is our last question, Lee. Any use cases of these solutions other than characterization, for example, assessing species erosion or predicting species erosion?
Not sure I fully understand. Species aversion, like landscape level, like like ecology kind of studies.
Exactly.
Um,
That's what I think this person means is in an area where you would have taken it 10 years ago and now you're taking it again and you can see the differences. Or maybe in an agricultural area where there have been traditionally certain species grown and then now you're doing it 10 to 15 years later and there's been species depletion or substitution, which is a
yeah,
little bit far from what you normally do, but just your thoughts on that. If there's
those are
application of
challenging
this
things.
technology for that.
One of the nice thing about satellite data, again, it doesn't have a lot of resolution. So species, you're not going to get down to the species level. It's a little bit like doing a RNA analysis of a soil sample, right? You get a profile and you go, we think that there's, roughly this much of actinomycetes and this much, you know, uh, uh, different types of species. Um, but it's very kind of raw. And so from satellite imagery, that's what you would have. But the nice thing about satellite imagery is you can go back and get satellite imagery from years ago. Now, it's not going to be very high resolution because the Landsat, the long-term satellites, they go back 50 years. Don't, I think the resolution on those is about 30 meters squared. So they're really big blocks. So they're really landscape level things. Some of the new satellites that have been around for maybe 5 or 6, 7 years now, maybe even 10 years, you can go back and get like 3 meter resolution where you have some granularity on a landscape. So, you're looking at things. The other thing, we do have a project with a group that's doing land remediation around oil wells. So it's oil well remediation. And so, we are flying drones over those fields, and they've asked us about sort of species recognition. We've talked about it. It's kind of expensive, right? Because it's a very hard thing to do. It can be done, right? We can identify the species. What kind of like what I was showing you in the tool. If I can I share again real quick?
Sure.
Um, that apologize. I know I was trying to get the last question, trying to get out of here. But if we go in here and let's say, let me just find a good trade real quick and do something like that. So rating plots. So this tool right here, what you could do is, that's the wrong date. Let's go back here, something like that, or even maybe something like that. So it's a little less. More like what you see in the landscape. So if you can sort of step back and envision this would be a landscape instead of a plot in a field, what you can see is if you have this kind of resolution, I could go in there. I mean, we don't do this right now, but I could probably identify that species, or I could go to an expert who could identify that species. And if we can identify that species and this species and this species, we could probably do some characterization. We could build a model, but we could also just use images. I mean, if you had somebody and you wanted, we could, send them these images, or, you could take the images, put them in the platform, and then somebody could manually go through and, kind of take a look at these pictures over time. So it's a way to do, you could, I don't know what that plant is right there that's flowering there, but that's a weed of some sort. Weed, I shouldn't say weed, right? When we're dealing with biodiversity, everything is a plant that's got some interesting genes.
Exactly. And this
But
was generated with a drone, this particular
this was with a drone. This was probably flown at relatively low altitude. I'm going to guess that it's probably a 20 megapixel camera. This might be a 20 megapixel camera flown at probably 15 meters.
okay. Yeah, this would definitely be able to tell you whether, in time, if you're taking this every year or every 5 years or every 10 years, whether there has been genetic erosion, whether there has been crop substitution, I mean, species change, or crop change. This would definitely be able to answer that question. Rather than a plot, it would be a field or a mountain or something like that. So wonderful.
Yeah.
Yes. Thank you so
And if
much.
you went back to the analyst, you'd have sort of a field, and you could do transect, sampling. You could send a drone out to take a picture at that altitude every whatever 100 feet. When I was doing ecology studies, that's what we would do. We'd run every 100 feet. We'd lay a square down and count all the plants in it, and things like that. And this would be similar, but you'd be capturing those images again in a more principled way and in a way that you could back check all of your data and things like that.
Wonderful.
Excellent.
Okay. Yes, thank you, Lee. I think with that, thank you so much to the participants for coming today, joining us, and generating very nice discussions and questions. And thank you to Lee for putting such a wonderful presentation and shedding some light in something that we've been wanting to do for a very long time, just have not had the expertise to be able to present it to us. So thank you very much for your time and for your explanations. And the last word goes to you as a goodbye for our
Well, it was a pleasure
here.
getting a chance to think about this and talk about this and really be able to communicate. I'm a big fan of biodiversity conservation, and so I'm really excited to be able to talk to you guys and want to have more conversations. So feel free to reach out to me. As I said, I left my email on the last slide. I'm pretty easy to find on LinkedIn or just the Hyphen website too. So thank
Okay.
you.
Thank you, everybody. See you next time. Bye-bye.
Take care. Bye.